we did the first slide, but I updated first slide a little bit. So let me talk about something I feel important. Yeah, so this slide, I changed slightly, but I want to look at this same problem from problem-solving point of view. Yeah. All right, so recording computer. Yeah. It's presentation computer. All right, yeah. First, still the introduction part. I want to explain the main reason we can use the power series representation for our ODE solution. Yeah. First, let's look at the equation. Yeah. So this is the special equation we want to solve, Legendre differential equation. Yeah. It looks similar to our old type equation we learned before, Euler-Cauchy equation, but the biggest difference is here. Oh, I need to change the pen color. All right, yeah. Yeah, the biggest difference is here. Yeah. Because the degree, here you can see the degree is different. 1 minus x squared. X squared term, degree 2, the 1 term, degree, what's that degree? Degree 0, right? Yeah. Yeah. So, yeah, you can see that. Yeah. So the hard part is this degree 0 makes this equation more harder to solve than the Euler-Cauchy equation. Yeah. All right. So the question is, how do we find a different way to solve? So we cannot use the way we solve the Euler-Cauchy equation. So here, let me recall the way. What's the way we solve Euler-Cauchy equation? Yeah. So here, let me put it in a good position to write on the screen. Yeah. Comfortable position to write on the screen. Yeah. All right. So here, recall the Euler-Cauchy equation. Sorry. Yeah. Yeah. Equation. All right? Yeah. The key step is let y equals x to the m. Yeah. That form, the solution form, this special form. This m, a real number. Not necessarily integer. Yeah. And actually, in general, it's not an integer. In general, it's not integer. Only in a very special case, it could be an integer. That's the special form of that Euler-Cauchy equation. But only one term. So simple. Only one term. Yeah. Yeah. All right. But here, this method won't work. Yeah. The reason is this 1 here breaks the structure. Yeah. Yeah. This 1. Yeah. Yeah. Let me mute my phone. Yeah. Here's something from my phone, so let me mute it. Yeah. All right. Then you have to find a different structure for your solution. Yeah. So here, the structure of this one won't work. Yeah. You need to find a completely different structure in order to make it work. Yeah. So here, the guessing the structure, this first step is very important. Yeah. All right. So our next question, we want to change our idea, how to find the appropriate structure for the solution function y. Yeah. All right. Yeah, I mean, so that something I mentioned last time, then I skip. Okay, but I only look at the new explanation part. Yeah. All right. Solution. Yeah. Here the solution, apply the power series method. Yeah. Power series. Yeah. First, I hope you know this power series. Yeah. Yeah. That's this form. Yeah. Okay. You can see our guess here, we want to use this new form to replace this old form. Okay? This new form to replace the old form. You can see how different they are. Yeah. You do comparison. Okay? The old form, you only see one term. One power function, x to the m. That's a power function. Yeah. But here, you have infinitely many terms, right? See? That's an infinite series. You have infinite many terms. That means you have a lot of freedoms you can use. Yeah. All right? The single term, you only have one freedom, that m. M is the unknown parameter you need to determine. Yeah. Here, let's look how many unknown parameters we need. All these A coefficients, all unknown parameters, we can, choose from, to make it. So we have a lot of freedom to be used. Try to fit in our current ODE equation. How about that? This idea. Okay? All right. Yeah. So you can see we have better chance, right? Yeah. If we use this power series form, we will have better chance to find a solution. Okay? Yeah. All right. Another difference. Yeah. The first difference is infinite many unknown parameters we can use. But another difference. All right. Another difference. This m term here is a real number. Not necessarily integer. Most of the time non-integer, real number. But each term in our power series, each term, the exponent number must be integer, right? Yeah. And it must be non-negative integer. Yeah. Even negative, because when we talk about power series, we do not allow the exponent of x to be negative, right? Yeah. So from 0, yeah, look at from 0, 1, 2, 3 to infinity. No negative. So that part, another important difference. That part, okay? But that one, we will delay. So that this importance actually is useful. Now, this view difference, our view of this difference is useful later. Yeah. So here, let's just hold a little bit. Yeah. All right. But the next question. So this power series. Yeah. So it's give us better chance. Yeah. The next question, we want to understand how much we can do by using the power series representation, right? How much we can do. Yeah. All right. So my question, let me state my question in this way. Yeah. For any ODE like this, can you always use the power series method to represent your solution? Yeah, that question, right? Yeah, how far? Oh, you can go, okay? Right? Yeah, yeah. So let's try to understand the potential of this power series method. Yeah, how strong it is. Yeah. All right. Yeah. So let's look at the important theorem, background theorem. Yeah, I mentioned last time So that's the Taylor's theorem. Yeah. Here I do not have a lot of space, so you can see the, the font very small. Yeah. Yeah. So this is the well-known Taylor's theorem. Yeah. Yeah. All right. The condition. So for what function? Here it's a f function. Let's look at condition. F is defined on some open interval I around A, some point A, and suppose nth derivative, n plus 1th order derivative, capital N. This condition is important. Exists in this interval. Then for each x not equal to A in I, there is a value z. Yeah. So z is used to estimate this remainder term, because you need to estimate that. That z value is used between x and A. Yeah. So that this formula. Yeah. You can look at this formula. All right. The first n plus 1 terms, you use the derivative. Okay. Yeah. Derivative. The last term, you need to use the n plus 1 derivative at the value z. Yeah. Yeah. So that's the well-known Taylor's theorem. Okay. Yeah. Here you can see, because this theorem gives us the important background information we need to understand this power series solution. How far we can go, how much we can do in the power series method. Yeah. All right. So this time I want to go a little deeper than last time. Yeah. So last time I didn't go this deep. Yeah. And the importance is because I want you to look at this question from the problem solving point of view. Yeah. So you just imagine in the real world situation, you need to solve a similar problem, yeah, but you get stuck here. So you want to find a new way to solve a new problem. Yeah. So here we are in that situation. Yeah. All right. So now, yeah, based on this Taylor's theorem, so we can see, but Taylor's theorem, you can see, still, when you connect to this power series representation, you can see, still not quite the same, right? Yeah. Still, you have some gap. You have some gap. You need to put more effort in understanding. Yeah. So what's that gap? Because this power series, you represent in using infinite many terms, right? Infinite number of terms. But here, this Taylor theorem, finite number of terms. Yeah. That's the biggest difference. Yeah. Yeah. All right. So then, let's imagine that. Let's look at this, last term. For that last term, think about where this function has higher order of derivatives, higher and higher. We increase that capital N number. Okay, let's imagine. Yeah, we increase that N number. The more you increase, the more terms you can use here, right? Based on the Taylor's theorem, more terms you can use. Yeah, all right. Then imagine, is it possible we increase that capital N to infinity? To infinity? Even that we have infinite many terms in this Taylor's theorem, right? Yeah, yeah. Or you see, going toward that infinite many terms. Okay? Yeah? All right. So the next question is, but in that way, you need to assume your function, your f function should have derivatives of infinite degree going to, so people call the infinite, well, how to say that? Infinite, infinite differentiable. Let's say this infinite differentiable. All right. Yeah. So people represent in this way. C infinity. Okay. C infinity. Yeah. The order of derivatives this function have infinite. Yeah. C infinity on this interval I. Yeah. Yeah. Can you imagine that? Can you imagine that? Yeah. C infinity. Is it hard to get C infinity? Yeah. Look at the E function. Is this C infinity? E function. If you can take, derivative any order, right? Yeah. C function, E function, sine function. Is this C infinity? Cosine function, C infinity. Okay. Yeah. Many functions you can use to get a C infinity function, right? Yeah. 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 All right. So here the question. Another question. How many functions we can use to represent use the C infinity function? Yeah. Yeah. C infinity function very nice, right? Yeah. By the Taylor's theorem, we can use infinite many terms. The more terms we use, the better the approximation, right? The more terms we use, the better the approximation. Yeah. Yeah. If it's a C infinity, then we can get a excellent approximation. Yeah. All right. But the question is, how many functions can you approximate by the C infinity functions? Yes. I mean, in our real world situation, yeah, we want, so think about this way. We wish to represent all the functions we deal with in the real world by C infinity functions. Yeah, so that's the best. Okay, approximate by C infinity functions. Yeah, yeah, yeah. It's true. Okay, yeah, we can do that. Yeah, approximate. All right, not exact. Approximate, very close to it, but may not be exact. Yeah. But the error is very small. Error could be arbitrarily small. Okay, approximation. Here we need to use the approximation understanding, not exact. Yeah, yeah. So this C infinity, this terms here in infinity, we need to use the approximation view. Yeah. Why? Because when you use your computer to calculate this function, you can only use finite many terms, right? You have to stop somewhere. Yeah. Nobody can use infinite many terms. So to be practical in the real world, you always need to do approximation of your final solutions. Okay? Yeah. So that means approximation, that's the practical way. Yeah. So we should accept it, approximation way. Yeah. All right, so here. Yeah. So with this background, now you can see when we use power series representation, yeah, power series representation, because it corresponds to that C infinity function. Yeah. And the C infinity can be used to approximate any functions that we encounter in the real world. All right? Now, so you have your confidence when you use the power series to solve these ODEs. You have the confidence. Yeah. So, okay. Yeah. All right. So let's continue. Let's do the work. All right. With that, first derivative. You can see we take derivative term by term. Yeah. Yeah. So here, term by term. Yeah. Look at what's the derivative of each term, okay? By the power rule. Yeah. Power rule of the derivative. Yeah. By the power rule, it's that. Okay? Yeah. So you do the term-wise derivatives, term by term derivatives. All right. But the question, But the question, yeah, all right, so here, because this whole summation is a y function, y of, variable function. And how do you know? Yeah, mathematically, so here, I help you, here, I want to help you understand better, the whole picture better. So here, there is a question. All right, how do you know the derivative, the function, y function, we take the derivative, equals summation of, for each term we take derivative? Is that true? Yeah, because we need to see mathematically if it is true. We know this way is a convenient way, right? Derivative. But how do you know these two objects are the same? So y prime object and this summation object, they are same mathematically. Okay? Yeah. So you need some mathematical theorem to prove it. Otherwise, you cannot assume that, right? You cannot assume that. Yeah, it can be proved. Yeah. So in our calculus class, calculus 2 class, it can be proved. But when you prove it, there is another concept you need to use. Here I have to mention convergence concept. Convergence. Because when you talk about power series, you need to make sure your power series is convergent in some interval. Yeah. So the convergence concept. Convergence interval. Okay. Yeah. So you need to find that convergence interval. Yeah. It may not be convergent everywhere. Okay. Some x value you plug in, it's convergent. For some x value you plug in, not convergent. Okay, divergent. If it's a divergent, think about it. If it's divergent, when you do this, garbage, because garbage in, garbage out, right? Because this place is garbage, divergent. This place also garbage. Okay. Meaningless. You cannot do anything. In the divergence interval, you cannot do anything. Okay? Yeah. So this convergence interval is important. Yeah. How to find convergence interval? Yeah, we have a formula. Okay? Later you will see. There is a formula. The convergence interval determined by all these A coefficients. Limit, okay? There is a formula. Yeah. Take the limit. Yeah. That limit will give you the radius, because convergent interval, you consider there is a center. Okay? Center. So left half, right half, the same length, so there is a radius. Okay? Radius of the convergence interval. We can calculate this radius by some simple formula. Yeah. All right. You will see that later. Okay. Then we can come back to this question. Inside the convergence interval, it is true. So the mathematical theorem, there is a mathematical theorem, tells us inside convergence interval, we take derivative, we can do this term by term derivative, also convergent. Inside the convergence interval, this summation also convergent. That's nice. That's all we need. So you can comfortably take the derivative. Okay? Because this side you assume you are working in the convergence interval. Okay? This side, when you work on it, you assume you are working in the convergence interval. Okay? Yeah. Because at the end, after you find all the coefficients, you can calculate the radius of the convergence interval, right? Yeah. So then you check, when you plug in your x value, make sure you choose the value inside convergence interval. Okay, not outside, outside, divergent. Yeah. So that's important. Okay, all right. Then first derivative convergent, same. We apply the same theorem. Second derivative also convergent for x inside the convergence interval. Okay, we have no problem. So we can do all our math manipulations. Okay, yeah, all right. Yeah, so this kind of thing I didn't talk about last time. Yeah, because last time I only have 10 minutes. I cannot talk this much, this deep. Yeah, all right. Yeah, so this time I give you more information. Yeah, all right. Let's do the work. Yeah, yeah. Straightforward calculation. Yeah, but you need when you work, you need to be very patient, step by step, do the calculation. Okay. Combine the like terms, yeah, yeah, carefully, yeah, all right, yeah. So here, because when you do summation here, you need to work on the summation. Yeah. Sometimes when we work on the summation, yeah. So look at the starting point, yeah. So from 0 to infinity, yeah, because our original from 0 to infinity, yeah. Then after you take first derivative, because the zero term first derivative, it's gone. So you can see this one starting from m equals 1. Yeah. Second derivative, because first two terms all gone by second derivatives. So starting from m equals 2, and from m equals 2. Okay, all right. But when you add them up, yeah, when you add them up, yeah, yeah, you can see. So you can see, all right, some of the summations starting from 2, yeah, some of the summations starting from 1, then starting from 0. Yeah. So how do you, yeah, because you want to combine the terms within those summations. If the starting point is different, then you need to do some special treatment. Okay, you need to do some special treatment. Yeah. All right. Yeah. Because, for example, for this summation, yeah, and for these two summation, for the starting point from 2, yeah, you leave there. Yeah, you leave there. Yeah. Starting from 0. You have 2 terms more, so you treat this summation as the some kind of base summation, some base summation. Okay, yeah, yeah. All right. Then compare this summation, 2 more terms than the base summation, right? 2 more terms. Right. Can you write those 2 terms out? Explain. So when m equal to 0. M equal to 0. Yeah. All right, yeah, so here, the k is this number, okay? You have k times a0, then where m equals 1, k times a1, okay? Then plus the remaining summation, m equals 2, k a m x m. Because in this way, the same as the base summation, okay? But you take out these 2 special terms out for special treatment. Yeah. Yeah. The remaining, yeah, same base, okay? You can combine them. Same. Yeah. Similarly, this one, the first term you take out, okay? M equals 1, 2m, so 2. So you have, yeah, so here, let me use the space here. Yeah. 2 times 1, a1. Oh, sorry. This, we should have x, right? Yeah, I missed the x. Yeah, x to the first. Yeah. All right. 2 times a1 times x, one term. Then the remaining is that, starting from 2, right? The terms. Yeah. Yeah. So in this way, we can combine all the terms in that summation starting from 2 to infinity. Yeah. Inside, we combine them. Okay? Yeah. So you can see we can take out one terms from that derivative term and 2 terms from the non-derivative term. Okay? The function term, original function term. Yeah. Yeah. So this is the typical way when we do the calculation. Yeah. We separate like this. All right. Yeah. So next, yeah. So here we haven't combined, right? Yeah. So we just write it in a different way. Yeah. So here you can see we do not use that m. Yeah. So here we change m to s. Yeah. Change m to s. Yeah. Okay. Yeah. All right. Then okay. Yeah. Sorry. S equals n minus 2. Yeah. Yeah. Yeah, sometimes we need to do variable change for convenience. Yeah, for convenience. Okay? All right. Yeah. So you change. But even you make that change, yeah, you still, yeah. All right. Yeah. Yeah, because, so here, look at that. So you change. When m equals 2, yeah. All right. Yeah. Okay. Yeah, that change. All right. n minus 2. Yeah. All right. So then, look at the first term. Yeah. Remember, so we take out, one term from derivative term. 2, yeah, this is one of the 2. Actually, we have 2 from this one, yeah. But we take the first one, yeah, adding together, 0. And the second one, yeah. Yeah, so here. Yeah, right. Yeah. So here, yeah, to see the details. Yeah. All right, let's go to the previous slide to see the details here. Yeah. So the calculation of this part, yeah, you need to be very careful. You compare term by term. Yeah. So when you work on by term, very careful. Yeah. So the calculation, usually takes a lot of time. Yeah. So I plan to do this because my goal, I want you to understand this method, and you have some experience to use this method. But to be more realistic, I won't give you too many questions of this part, yeah, because it's too much work, yeah. So my basic idea is I just want you understand how to apply this method. And you have some experience, that's enough. Yeah. Yeah. But when I give you homework questions or final exam questions, I will not give you too many. Okay? Yeah. Just enough to get experience. Yeah. 1 or 2 questions like that. Okay? Yeah. All right. Yeah. So here, yeah, when you work on this equation, both sides you compare term by term. First, look at the x0 term. Both sides, x0 term must be the same, right? Yeah. So right hand side always 0. So the left hand side, s equals 0. So you add up all the terms for s equal to 0. It should be 0. Okay? All right. S equal to 0. Here you plug in 0. Yeah. 2 times 1 A0. So the contribution from this summation, you have 2A0. Okay? All right. S, yeah, because S must be 0. So we skip this summation, right? Because no contribution from that summation. Starting from 2, yeah, so no contribution. Starting from 1, no contribution for S equal to 0. Then one term contribution. Yeah. S equal to 0, K times A0. Yeah. K times A0. That equals 0. Okay? Yeah. Then you can see from our next slide, so this one, yeah, that's that equation. Okay? Yeah, because this is K. This is K. Yeah. K times A0. Yeah. 2 times 1. Okay? Yeah. So that's the reason we get first equation. Okay? The second one, yeah, second one, we also need to find the second one. Let's go back to see the second one. Okay? Yeah. Yeah. Otherwise, I hope you won't, you do not get lost, the second one. Second one is for S equals 1 this time. S1. Contribution from the first summation, you plug in S equal to 1. Okay? All right. 3 times 2, right? Yeah. 3 times 2. 3 times 2 is 6. Okay? 3 times 2. A sub 1 plus 2, A3. Yeah. Contribution from the first 6 times A3. Yeah. Contribution from second summation, nothing. Yeah, because S starting from 2. So second term, nothing. Okay. Contribution from third summation, S equal to 1, 2 times S1, okay, plus 2 times A1, right? So contribution from the last term, S equals 0, S equal 1, plug in 1, K times A1, okay, yeah, plus K times A1 equals 0, okay, yeah. 2 and the K you can add in together, 2 plus K, yeah, because for the same A1 term, yeah, yeah. K plus 2 times A1, yeah. So let's compare with the next slide, yeah. Okay, see, this, minus, yeah, plus minus, yeah. Yeah. All right, look at this minus, all right, yeah, yeah. So here, this should be the minus, yeah. Here you can see, very easy to make mistake. Question. Yeah.
When we have the substitution for S is equal to n minus 2, you applied it to the first term. Why not the second term? Why not the series both start with 2?
All right. Okay. All right. So yeah. Let me answer your question. Yeah, that's another important step. Yeah. I need to. So this equation comparison we passed, right? Yeah. So we passed in the video. You can, if you want to watch, you can, rewind, watch, because I need to erase this part to explain Matthew's question. Yeah. We need some, small space to explain. Yeah. All right. Now I want to explain. When we do substitution, S equals n minus 2. Yeah. So Matthew's question. All right. Yeah. So can you say again? Yeah. Your question.
Yeah. We applied that substitution to the first term, the base.
Right. Base. Right. This.
But not to the second term.
Oh, not to the second. Okay.
Because they both start.
All right. How about this? Let me apply one by one. Okay. Then let's see if your question can be answered. Yeah. Let me go through the details, summation by summation. Let me show you. Okay. How to get first, second. All right. All right. Yeah. So S equals n minus 2, the substitution. When m, so here, when m equal to, let me write. When m equals 2, S equals 0, right? Yeah. First, let's look at the, starting point. M equals 2, the same as S equals 0. Yeah. So that's easy. All right. Then this m, because m equals S plus 2, right? S plus 2. So we replace original m by S plus 2. Replace n minus 1 by because minus 1. Okay, this number minus 1, so s plus 1. All right. Then m should be s plus 2. All right. Then this exponent, n minus 2, that's s. So the first term, no problem. Okay? Understanding. Then the second one. Second one, oh, yeah, all right. Now, so you have question on the second one? Summation? All right, yeah. Let me answer that, the point. The point is there are many zeros, okay? Yeah, so let's start. Yeah, all right. Let me do one by one carefully. Yeah? Let me also erase this part. I need a space. Yeah, all right. I need a space. Yeah. All right. All right. Then let's carefully plug in one by one. Okay? All right. All right. When m equals 2, oh, sorry. Oh, 0, no 0. Okay? All right. Yeah. No, yeah. So, all right. Yeah. Yeah. Whatever. Let me just try it. Okay? All right. Yeah. Yeah. All right. There is some problem, not 0. There is some problem. Yeah. All right. Yeah. So let me do direct substitution first. Yeah. Is it? Yeah. Because s equals 0, infinity, yeah. M s plus 2 s plus 1 a s plus 2 x s plus 1, right? All right. All right. Yeah. Okay. Oh, sorry. S plus 2, right? Oh, yeah. All right. Now, okay. Let me explain. Okay. All right. Another substitution. Can you imagine the second substitution? Yeah. First after first direct substitution, we get that one. All right. Now, because the thing is, the general term is like this, but the general term here is x to the s. General term is x to the s plus 2. They do not match. Because we want our general term in the representation s, not because 1s, the first summation general term, second summation s plus 2, they are not compatible. Okay, if we add them together, how can you add, right? So we want to make them compatible. So we want to make this look like, let's say x to the S1. Can we change to a different variable? Because this variable is dummy variable, right? S1. S1 we can replace, go back to S, right? Because that counter variable, it's a counter variable. We can use any variable, right? Yeah. After we replace S plus 2, yeah. Here you can see we go back to M, right? Can you see we go back to M? Yeah. Here, this S2. Here, yeah, that's why it's very confusing. Yeah, because this formula I cut from the textbook. Yeah, screenshot cut from the textbook. Okay, yeah, yeah, because this S2, you can see, is it here S equals M? If X equals M, you have no problem, right? Yeah, yeah. That's why it's very confusing, because in the textbook it says we use x equal. So s equal m minus 2 for the first summation. For second summation, our s is different.
Okay, so we're allowed to do that. We use different substitutions for each.
Yes. Yeah. For each summation, we can use different substitution. All right? Yeah. Because each summation is independent, right? Each summation has nothing to do with other different summations, right? You do your own summation, okay? You use your own subscript variable, let's say. Yeah? We change S, M, T, whatever, you know, you can do. That's the point. All right? Yeah, that's the point. Okay, good. Yeah, I think we clarify that question. All right. Yeah, so here, yeah, let me write, yeah, still right here. Yeah, yeah, you know, for your, you know. Then the summation, is it the same? Right? Yeah, you know, S equals M. Same. Yeah. That, still the same, right? Right? Yeah. 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 Only the first one is different, okay? The first one we use S equal to M minus 2. The remaining three, we all use S equal M. Yeah. The reason is because we want that general term, the same degree or order, same order for the general term, okay? X to the S, X to the S, X to the S, X to the S.
So the starting point for each one doesn't need to be the same?
Yeah, starting point,
Okay.
usually different. Starting point, we can align, right? Yeah, starting point, we can handle, you know, process, you know, as special cases, But we only want to make the general terms, you know, same, yeah, same form, okay? Then we can combine we can add up the coefficients. Yeah, that understanding. Yeah. All right. Yeah. So based on, we're at the break time. Yeah. Yeah. Although we move very slow, because this part is important. After you get over this part, then you do your homework. You know, questions. Then it's easy. Yeah. All right. So we were rather going a little slower. Yeah. After that, just the algebraic calculation. Okay. Yeah. Although it's still, you need to do a lot of work. Yeah. But you know, you can handle. Yeah. All right. Let's take a 10-minute break before we continue. Yeah.